Gas turbines are able to run on a whole lot of fuels beyond just what we consider traditional natural gas or LNG. If it's a hydrocarbon, we most likely can burn it.
This is EnergyCast, and I'm Jay Downhauer. Today we are talking about combustion turbines and the emerging diversity of fuels we can expect to run them. As my guest notes at the top of this interview, the terms combustion turbines and gas turbines have been used interchangeably. Most of these turbines have been fired by natural gas. As my guest also notes, more turbines are using waste natural gas, industrial gases, and even hydrogen. The first combustion turbine in the U.S. was placed into service by my guest's company over 70 years ago. Its technology is derivative of jet engines. If you grew up in the 80s like me, you remember commercials like these.
Build me an engine that can carry me home.
Yep, 747 landing.
Light my darkness, bake my bread.
At home in the kitchen. The same technology to fly you across country can also power your homes, was the message. Today, natural gas makes up the largest amount of installed electrical capacity in the United States. Combustion turbines, either alone or combined cycle, that's with steam turbines, make up about 80% of these installations. And no wonder. Natural gas is cheap, probably the lowest it's ever been. As we've discussed in the past, combustion turbines can provide the most power, the quickest of any baseload technology, like coal or nuclear, which are both steam-driven, and it's important as renewables come online and we need quick, reliable power to balance out their intermittency. That's another reason why I said natural gas was the largest installed capacity. It's used to peak a lot of the times, not run full out. Of course, that also could change. My guest believes combustion turbines could also hold the key for hydrogen's future. You've heard me talk a lot about using hydrogen as a storage medium for surplus energy like renewables. These turbines could easily be fired with hydrogen, which on its own doesn't produce CO2. Of course, the key is producing enough hydrogen consistently. If hydrogen is produced by too few intermittent sources, then hydrogen itself becomes intermittent itself. And it's this drive to find ways to balance out the grid and use all the many fuels available that even those that have been formerly flared off are leading to a cleaner, greener energy future. My guest today is Jeffrey Goldmeer, Director of Gas Turbine, Combustion, and Fuel Solutions for GE, a small startup founded a couple of years ago in New Jersey. You know, I kid. In fact, when we were doing the lightning round at the end of this episode, I don't think there was a single energy family GE did not participate in. I first met Jeffrey at PowerGen in New Orleans last year. I made 2 presentations at that show, and Jeffrey was my session chair for both. At the time, Jeff described his role as developing any solution for combustion turbines that did not involve natural gas. Just coming off a presentation touting hydrogen, I was intrigued. We also talk extensively in this interview about a solution for excessive flaring on natural gas sites, which I'm a big fan of. I hope you enjoy my conversation with Jeffrey Goldmeer. We're here with Jeff Goldmeer, Director of Gas Turbine Combustion and Fuel Solutions for GE. And Jeff, in the old days, gas turbines meant natural gas. Now your group is promoting all kinds of fuels for turbines. What's changed?
You're correct. Most people kind of associate the name gas turbine with natural gas. So it's true that most gas turbines that are operating today run on natural gas. But gas turbines are able to run on a whole lot of fuels beyond just what we consider traditional natural gas or LNG. And they've been doing it for decades in all sorts of power plants, supporting not just utility scale power generation, but also industrial scale applications. And it turns out we've got more than 400 gas turbines. They've run for millions of hours on these, we'll call alternative fuels. That's not natural gas, not LNG, not diesel. The other thing that's really interesting, it's a bit of trivia that I learned a couple of years ago. We have many customers in the industry who don't call them gas turbines. They call them combustion turbines because what are they doing? They're taking the chemical energy in the fuel, converting it to electrical energy through a combustion reaction. So they differentiate between a steam turbine by calling it a combustion turbine. And so I think that's It's not a name I hear used often in industry, but I think it's very illustrative of nothing's really changed. It's a device that you use to convert chemical into electrical energy.
And so what other kind of fuels are we running through these combustion turbines?
We run a lot of different fuels. Again, most parts of the world, it's natural gas or LNG. In some parts of the world, it's diesel. In some parts of the world, we're going to be looking at different grades of crude oils. In some cases, it might be a biofuel. In other cases, it might be a natural gas that's got some additional nitrogen or CO2 or some sulfur in it, all sorts of industrial type fuel. So really, if it's a hydrocarbon, we most likely can burn it.
Yeah, Jeff, I'm a big supporter of eliminating waste. It would seem that one of the big applications here is making use of combustible gases produced from industry. You got a big factory, that's where you would be able to make use of that gas that's kind of offshooting.
Absolutely correct, Jay. Gas turbines can run on a huge variety of fuels, including some that we might call waste products or byproducts from all sorts of processes. And if you're running an industrial plant and you have these gases, you might say the simple way to deal with them is I'll just flare them. But if you can flare them, that means they'll support a combustion reaction. So in some of those scenarios, what those customers will do is that, like, instead of flaring that gas, I could use that gas to produce power, support the house loads of my process. Maybe I make some additional power more than I need. I can go sell it on the grid. And since you were going to flare those gases, they're effectively free. And we see lots of examples of this, whether it's the steel industry, petrochemical, plastics, all sorts of industries where this kind of example holds. One example is we got a power plant in Asia where they've been running a waste fuel into a gas turbine for more than 20 years. This is a model that has been duplicated over and over again all over the world.
Speaking of flaring, I did an episode about reducing flaring at oil field sites. So it's something that really annoyed me for a long time. Now, how would you best deal with that issue? And I think one of the big issues with oil fields is, especially places like North Dakota, is they're pretty spread out. And they're pretty remote and not really next to industrial centers.
Right. So clearly a key aspect there is how much are you flaring? And then you've got to capture that gas. And to your point, it's not like it's one site. There are lots of sites and they evolve over time. You have to capture that gas. And then you have to have a gas turbine that's scaled for the application you're looking at, right? So it's not necessarily going to be a gas turbine that's a 400 megawatt gas turbine. You're going to look at a gas turbine that's smaller on our portfolio, these 20 and 30 megawatt gas turbines. And this really has a lot of power, not to use a funky phrase here, but just the power of leveraging the technology to solve a problem. We have an example. We got a project in Africa where fundamentally they've got isopentane coming off an oil field or gas field. Instead of flaring it, they've decided, let's go put it into a gas turbine. So we've got a project in development where we'll use that isopentane that would otherwise have been flared to deliver something on the order of like 25 megawatts of power to the community. But part of the trick there is, right, scaling the gas turbine for the amount of fuel you've got.
Yeah, we've also discussed this concept of blue hydrogen from natural gas. I've asked this question before with other guests. What's the incentive to make hydrogen from natural gas? Why not just combust the natural gas itself?
So I think the question comes like, why don't we just continue with what we're doing today?
Sure.
And I think a lot of it just comes down to the fact that if we look at the global conversations on climate change, and one of the outcomes coming from those global conversations is to decarbonize many industries, including power. If your ultimate goal is not just to produce power, but to produce power that has a lower carbon footprint, how do you do so? And now you get into the conversation of, well, is it the blue hydrogen, which for the listeners here, we're talking about how do you take something like natural gas, you reform the natural gas, you get both CO2, carbon dioxide, and hydrogen. You take the CO2 and you do something with it, use an industrial process, you use it for enhanced oil recovery, you sequester it, you do something, but then you then take that hydrogen. Now that hydrogen's a carbon-free fuel, and so you can go burn that. And the incentive there is you're reducing carbon emissions. Again, as long as you take that carbon that you pulled from that natural gas and do something with it so you just don't release it back into the environment. There's blue hydrogen and then there's green hydrogen, which is hydrogen from electrolysis that is supported by renewables. Ultimately, it's hydrogen, but the incentive is to decarbonize or reduce the carbon emissions from the power cycle.
That green hydrogen, that was something we started talking about back when we first met at PowerGen last year. I mentioned in one of my talks during then an episode about offshore hydrogen production from renewables, specifically offshore wind. How do you feel about the hydrogen market and how close we are with this idea that you would take excess renewables and start spinning it into hydrogen?
So my view, I think we can break this into three elements. There's technology, there's infrastructure, and then there's the economics. Let's talk technology. So what we're fundamentally talking about is taking excess power from wind turbines or from solar fields or renewable power sites, converting that to hydrogen, and then taking the hydrogen and bring it to a gas turbine. When we think about those pieces, they exist today. Gas turbines today can burn hydrogen. We've got a gas turbine that over its lifetime has burned a fuel that's had almost 100% hydrogen for many years. In fact, we also demonstrated on a project about 10 years ago that a gas turbine could actually run on 100% hydrogen. I think if we think about technology, the fundamentals all exist. But the next question is, how do you translate that and transition not just to small pilots, but transition to now, let's call it utility scale production, transport, storage, and use of hydrogen. And that requires new infrastructure, right? If you think about taking a lot of gas turbines and making hydrogen for them, but the hydrogen comes from offshore platforms, how do you put that entire infrastructure together? What are the investments required to do that, at a national level? And the scales are large. So let me just put in perspective. So if I looked at a 6B, which is one of our smaller gas turbines, can run either on a 50 or 60 hertz grid. It's a gear turbine. It generates about 44 megawatts. If I was going to run that gas turbine on 100% hydrogen, I would need something just under 40 million cubic feet a day. That's a lot of hydrogen. Now you think about how many turbines you have at larger scale. How do you build out the infrastructure to make that much hydrogen? You can also store hydrogen, but if you want to store it cryogenically, there are some challenges there. To store it cryogenically and make it a liquid, you've got to get temperatures lower than 400 degrees Fahrenheit. So infrastructure challenges are there. And then let's talk economics. Today, hydrogen costs significantly more than natural gas. If you were looking at blue hydrogen, maybe you were in the range of $20 per million BTU. If you were green hydrogen, maybe you're $50 per million BTU. I've seen numbers saying maybe it's as high as 100. For reference, natural gas is somewhere about $2.50 per million BTU. So an order of magnitude differential. Again, technology, infrastructure, economics. Infrastructure is doable with the right investment. The technology is there. It's now about the economics.
I think one of the points I'd point out with that Tractable episode, and that was the company that was developing the offshore hydrogen production, they were specifically making hydrogen. That hydrogen could be produced to sink excess energy production rather than make it deliberately. Those periods of the day where your solar power is generating more than you're consuming. There's a difference there rather than producing it deliberately. So does that affect the economics? You brought up this blue hydrogen versus green hydrogen and the price. It's more expensive to do green hydrogen right now. But this idea that you're just doing it as more of a way to sink the electric production, it's wasted electricity production, so why don't you making it with hydrogen? Does that affect the economics one way or the other?
Absolutely can. So let's think about the scenario. So I've got a large solar field or wind field, and I've got a scenario where I'm creating more than I need. So supply is greater than demand. If you're not curtailing the wind or solar, effectively, you've got a glut of power. And there are scenarios today where you'd see people will talk about negative power prices. Consumers, that demand side, they're going to be asked to take power, and they may get paid to do so. The concept is when that happens, if you have an electrolyzer becomes a load to balance the grid. You've kind of level set that negative price. You put that power into the electrolyzer and you make hydrogen. Now, whether you use that hydrogen for an industrial purpose, you use it for transportation, i.e. hydrogen fuel cell, you can generate enough for a gas turbine, but you can absolutely do that. But the trick is you've got to make sure what is the amount of hydrogen you're generating as your supply versus your customers, their demand scale. Well, you're going to be limited because it's not 24 hours a day, 7 days a week. It's going to be some discrete periods, an hour here, an hour there, maybe a couple hours mid-afternoon before everyone comes home from work. The sun's shining pretty bright if you're a solar field or something, which limits the amount of hydrogen you make. So there are some trade-offs in that scenario. The other thing we have to think about just fundamentally is how much of that curtailed power really exists and how much hydrogen can you generate from that rationally. At least the math I've done says today, yes, there is curtailed power, but you're not going to really generate as much hydrogen as you think if we're thinking about a power gen application. Again, because the windows of curtailment are pretty small.
Yeah, you're thinking the hydrogen would be used for more of like small fuel cells, something like that, right?
Right. We're talking about a world in 2040 or 20, the penetration of renewables is significantly higher than today. Conversations I've had with some folks say there may be periods of the time during the year where there will be significant curtailment just because of how much renewables it's been built out. So this concept could develop over time, but it's a difference of a 2020 view maybe versus a 2040 view.
Sure. And I think it's kind of interesting that one of the biggest problems with electricity production from renewables is intermittency. If we start really depending on that hydrogen that they're producing, that will also be intermittent.
Right. And one of the things I love about hydrogen is, to me, hydrogen's a way to time shift renewable energy. If you can make hydrogen and store it, you can store it for very long periods of time, and it lets you time shift that I think of hydrogen in many ways like a chemical battery.
You were featured in a Bloomberg article earlier this year. One of the challenges of combusting hydrogen is that it produces nitrogen emissions. This was according to the article. They called it nitrogen emissions. I assume they're talking about nitrogen oxides, NOx. Does that mean that we need to include scrubbers for hydrogen combustion turbines? I think you just kind of think hydrogen being super green, but there are some emissions that come off of it. It'll naturally react with the nitrogen in the air.
Correct. So let's be clear for the audience. Anytime you're burning a fuel and air's got nitrogen, you'll make NOx.
Yeah.
So if you're running a gas turbine today and you're running it on natural gas, there are NOx emissions. GE, along with other OEMs, have technology that lets us run these combustion turbines with very low NOx emissions, technology that we have developed over decades. The challenge with hydrogen burns at a hotter temperature than basically any other fuel. And it turns out that NOx emissions are not just related to temperature. The amount of NOx you make is an exponential function of temperature. So as you burn something hotter, you'll make more NOx. So yes, if you're running a turbine on hydrogen, you have the potential to make more NOx. But since many gas turbines today are going to be running with, we'll call them scrubbers, but they're really a post-combustion after treatment. The technical term is a selective catalytic reduction system, SCR. They're pretty commonplace in the industry. There's no reason why, if you were going to switch from running your gas turbine on natural gas to running on, let's say, a blend of natural gas or hydrogen, you couldn't use the same technology to reduce the incremental NOx. And I think it's important. It's incremental NOx that we're talking about here.
Sure. And as far as your turbine technology, I'm assuming that as more of these non-natural gas, non-methane gases are being considered, especially things like hydrogen, can you retrofit them? Do you need to just swap it out for a different turbine? Can you run landfill gas or hydrogen in a conventional combustion turbine?
It's a great question. One of the great features of gas turbines is they're incredibly flexible when it comes to fuels, and they've got hardware and systems that can be upgraded over the life of the asset. So if someone's running a gas turbine today or combustion turbine today running a natural gas, first thing I want them to know is that gas turbine, as it stands today, could burn some percentage of hydrogen blended in with that natural gas. It's just a matter of how much. And as you want to cross that limit, now we talk about what are the upgrades that are required. Is it I have to go swap out the existing combustion system for one that's capable of burning higher amounts of hydrogen? We talk about safety systems. Hydrogen, because of some of its characteristics, it's different than methane. It's more flammable. Its flammability range is wider. There's a whole range of safety-related things that we would look at. These are things that we've actually been dealing with for decades because of our experience in these industrial-type fuels that contain hydrogen. This is not new. We've dealt with these challenges before. We know exactly what kind of subsystems need to be upgraded. And so, yeah, you could take a gas turbine today that's running on natural gas, and if a customer said, hey, I expect to get hydrogen from some source, and I want to start burning a blend 20%, 30%, 40%, 50%, we could walk them through exactly what needs to be changed on the upstream accessory side, piping, valves, control systems, et cetera, what you need to do to the gas turbine in terms of the combustion system, what might the impact be to post-combustion after treatment, depending on how they're permitted today. In fact, we actually have that kind of conversation on a regular basis with customers who are trying to understand the impact of hydrogen and decarbonization over the lifespan of their turbine.
One of the things we talked about off air was you mentioned there is an aeroderivative gas turbine technology. Why is that exciting to you?
Aeroderivatives are really cool. So fundamentally, if you take the core of a jet engine, and a jet engine effectively at its heart is a gas turbine. But if we took that off of the aircraft and configured it not to generate thrust, but to generate power, that's an aeroderivative. These are relatively small gas turbines if we think about the size of a conventional jet engine off of, let's say, like a 737 kind of aircraft. We package them up. They're relatively small enough. I can ship them via an aircraft like an Antonov. I can ship them all over the world. One of our models is trailer mounted, which means it literally is on a trailer bed, so we can, take it off the airplane and drive it to site. It's highly modular. It can be installed in just a couple of days. And the reason that gets me excited, I want to go back to our question on flare gas.
Yeah.
So think about these oil fields. They're going to have a byproduct of gas, or gas fields where they're producing more gas and they're flaring. We talked about, right, those fields evolve over time. They're not going to have the same amount of gas over a lengthy period of time. And one of the concerns is, okay, if I'm going to go put a gas turbine in for consuming flare gas, if that part of the field or the field I'm working on, the amount of flare gas over time decreases because I basically consumed that pocket of gas. Well, with a stationary power plant that I put concrete footers down and foundations, I can't move that power plant really easily. But with a trailer mounted unit, once I finish consuming that gas in that pocket or that section of the field, take a day or two, pack up the gas turbine, drive it to the next location, spend a few days, reconnecting all the modules, and there you go again, you're making power. So when you think about these kind of applications like a flare gas where modularity is important, that's wonderful. And another application where these gas turbines have had a lot of value is in situations with devastating natural disasters, so that'd be hurricanes, tsunamis, earthquakes, etc., where existing infrastructure is damaged. The power plants are damaged, but you need critical power for infrastructure, for hospitals, etc. And you can fly these units in, and with just a matter of days, they're up and running, providing power in these what are otherwise just horrific situations. So there's a lot of value in having these very small modular gas turbines because they're coming off the core of a jet engine. And you think about your time on an airplane, you're sitting in the airplane, it's time to take off, the pilots turn on the engines, you can hear those engines spool up very rapidly. The same thing with them when they're in a power application. They can spool up very quickly. They can load follow really well. So they've got other benefits in terms as we think about grid following. If we're looking at power systems that can be put in place in tandem with renewables and supporting the variability of wind and solar. The larger gas turbines can do it too, but there's some value here. So these smaller aeroderivative gas turbines have a lot of value just because of kind of their history, their legacy, and their size.
Well, it certainly is interesting, especially when you're talking about it being mobile. And as someone who spent a lot of time on oil field sites, especially following fracking operations, I can tell you there's not very much that's on a concrete footer. Most of the stuff is on rubber tires and trailers because it's going on to the next location.
We actually just demonstrated at our factory the ability to demodularize and then hook up this power plant on wheels in just a few days. There's this really cool YouTube video out there. They've kind of time lapsed it to show how fast it is to turn around one of these things from producing power, uncoupling it, drive it off site, drive it back on site, and put it together. It's days. It's like 48 hours. It's absolutely amazing.
That's really cool. I'll make sure we link that video on our site. Jeff, I'm going to finish with a lightning round of your thoughts on different energy technologies. As I'm looking through all of these, I'm thinking there's probably not very many sectors here that GE doesn't touch. So this should be pretty interesting. We'll see how you think they all fit in the mix. Starting with natural gas.
It's a great fuel supporting power generation all over the world. It's available in large quantities and at record low prices and offers all sorts of benefits around efficiency, power density, and reliability. So love it.
Crude oil.
Let's think about it. Fundamentally, it's a foundational hydrocarbon for much of our society today. It's a key for transportation. It's a key for production of many of the things we use. But that might change as we think about electric vehicles and fuel cell vehicles. What does that mean for crude oil in the future?
Nuclear.
A carbon-free power source that many view as critical for a carbon-free future.
Coal.
In the U.S., we see a transition from coal to natural gas. It's talked about a lot. But if you look outside the U.S., it's a fuel that much of the world still depends on for power. And it does emit more carbon than natural gas, but what's beyond that can be addressed with the appropriate emissions treatment systems.
Wind.
A transformational technology. It's changing the way the world thinks about power.
And you guys also have the largest wind turbine ever built, right?
We do. Allied wind turbine, yes.
Yeah. Solar.
Like wind, I view it as a transformational energy. But like wind, there are real limitations that have to be addressed. There's real variability in both wind and solar, and that's critical with something to be addressed.
Biofuels.
It's an interesting opportunity for power generation and transportation. One, I think that's going to be very regional specific.
Hydroelectric.
A technology that's critical for power generation in many parts of the world. I personally think it's even more powerful if you couple that with pumped storage.
Yeah, big fan of that. Geothermal.
It's a wonderful carbon-free source of heat and power, but one that really might be limited in the scale of opportunities.
Energy storage.
A key for the future. I think I mentioned it earlier. I think of energy storage beyond just batteries. If we really are able to couple production of hydrogen from renewable power, it's a way for us to store that energy in a way to time shift it away from, let's say, the summertime. We may have abundance of solar to the winter when we might not have all that solar available.
Yeah, I definitely like the point that it's not just batteries. Electric vehicles.
I love the idea, but as we think it through, we have to think about what it means in terms of new infrastructure and new sources of electricity. The assumption in my mind is that an electric vehicle means that the goal is not to shift from gas engines in my car to electricity from fossil fuels. The goal is to shift from fossil fuels in my car to an EV vehicle that's being powered by renewable power.
And since we're talking about hydrogen, I did want to point out the difference between electric vehicles and, say, like fuel cell vehicles. So any thoughts on what may win out or how that balance is going to work in the future?
I think a lot of that's going to depend on infrastructure. The ability to have an electric vehicle that assumes that you've got a plug. You can plug your car into the system at home, the recharger at home, the recharger at the mall. cetera. A fuel cell vehicle means that we have hydrogen infrastructure. And so, again, two different infrastructures. And I think there's, in some parts of the world, they're leaning towards one versus the other. There are some definite benefits to fuel cells. I know I listened to your episode with Plug Power. Mm-hmm. It would definitely say that there's some real advantages to a fuel cell vehicle because you can refill that tank or recharge them very quickly relative to the charging time, let's say, on a battery.
Energy efficiency?
Well, this is the easiest place to start to think about reducing our carbon footprint. It's something you and I and your audience, we can all do at home. In the power generation industry, updating existing power plants to operate more efficiently and therefore reducing their carbon emissions is something we can do today. And at GE, we continue to develop new gas turbine technology to increase the efficiency of our gas turbines. GE is proud that we actually have 2 Guinness World Records for gas turbine power plant efficiency.
And then finally, fusion power.
It's not my area of expertise, but my personal view is it's probably a long way off if it's even possible to do at scale.
All right, Jeff Goldmeyer, GE, thank you so much for your time.
Jay, loved it. Thank you so much.
That was Jeffrey Goldmeyer, Director of Gas Turbine Combustion and Fuel Solutions for GE. Jeff also showed me some entertaining cartoons GE has produced with him as a character, so if I didn't explain things well enough in this episode, you can bet they definitely did a better job. I want to thank Jeffrey and GE for their time and cooperation on this episode. You can find plenty of pictures online at energy-cast.com as well as on Instagram at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 82. Be sure to join us next week when we discuss how the Department of Energy is making enhanced geothermal a reality. Until then, I'm Jay Downhauer. We'll see you next time.